Well, hello everyone, welcome back to Adrian's Digital Basement. On today's video, we're revisiting the Zenith ZT-1. This is going to be part 4 in the series where I try to get this terminal working. As per usual, if you haven't watched the first 2 or 3 parts actually, before seeing this video, I recommend you do that first because we'll be continuing off with the repair saga right where I left off. As a quick recap, the Zenith ZT-1 is a 1982 home/business terminal device that was designed to allow people to connect up to modem-based information services without having to have a computer. At that point in time, having a computer was relatively expensive, so this thing just allowed you to hook it up to a television or a monitor and then dial up over a 300 baud modem to these information services. The one that I got here was in absolutely pristine shape, but unfortunately it wasn't working. It appears that someone had tried to work on this thing before and decided to give up and just put it back in the box. And when I got to it, it really seemed to be completely dead. It wasn't showing any signs of life. In addition, after a little bit of troubleshooting, the power supply gave up the ghost as well. That turned out to be a shorted tantalum, which I was able to fix. And then I got back to troubleshooting the symptoms of the computer not working at all. And it turned out that it appeared that the system was actually initializing, but the video chip, or the CRTC, didn't appear to be working. It was this chip in my hand. It's made by Intel 8275. And when I put the replacement in, the Siemens part kind of worked. The thing showed signs of life, and I was able to get into the menus. We still had some issues with the display on screen. So in part 3, I used a logic analyzer again to try to figure out exactly what was going on with communication to the CRTC, the new one that's in the machine. Well, it looked like everything was working absolutely perfectly. So I went ahead and I ordered another chip, thinking that the Siemens part that I put in there was bad, so I got an Intel 8275 replacement for the bad one. Hopefully this inside the machine brings it back to life and allows it to fully operate. And if that's the case, the machine does fully work. I have a to-do list of things I want to test out, including testing the modem and trying to figure out how the serial port stuff works on this, because it looks like after some hand disassembly and reverse engineering of the ROMs, it appears this thing actually has a built-in serial port. It just wasn't mentioned anywhere in the manual. So if the machine does actually work and the modem works, then I want to see about that serial port, and maybe I can hook up a Wi-Fi modem and get this thing online. So there's a lot to do in this video. If the machine does actually work, so I need to stop talking about it and we need to actually get to work. So without further ado, let's get right to it. So this is the Siemens 8275 chip that doesn't seem to be working, which I think is not compatible or potentially bad. And everything else about this machine is 100% original, except for the one tantalum I swapped out over here because that's what shorted and took out the power supply. Do still have the nickel metal hydride battery connected to retain the phone book entries, and it's running the original SRAM chip that would be storing those phone book entries. So it's been a little while since I've had this machine powered up. It will be really interesting to see if we still have our phone book entries after maybe about a week or so. So this top chip is the Intel replacement 8275 I bought online. It does look a little bit different than the original. And this has a 1976 date code, and that says 1985. So I hope they're fully compatible. For looking at the video output, because I want to just test to make sure this thing still has the exact same fault we left off with in part 3, I have the video output connected to the RGB to HDMI, which is what we're looking at here. And let me turn on the power supply, and let's hope that we see exactly the same fault. Yes, we do. We are missing the P on press. And yes, that entire left column over here is missing, so good. Nothing has changed, because it would have been really annoying if the problem had just suddenly gone away while I wasn't using this machine. Out with the Siemens 8275. In goes the new chip. Oh boy. Come on, are you gonna work or are we gonna have the same faults? I'm gonna cross my fingers. Because I cannot deny that if this doesn't work, I'm kind of at a loss as to what might be the problem. But it's making sure it's in the right way, it is. Here we go, 3, 2, 1. Oh no, the problem is still there. There was nothing wrong with the original chip. No way. Yeah. Wow, okay, well, I didn't mention before the phone book entry is still working, so that battery definitely did the trick. So if I want to put a new NiCad or a nickel metal hydride battery in here, all I need is a single 1.2 volt cell, just like I have there. But we have not fixed the machine. We have some other kind of timing issue that I could not identify in the last video. Well, let's type out some stuff here. I'm going to type a bunch of 1s, and I want to see if I go all the way to the end and we type some other letter. Am I going to have that same behavior where it was giving that first character that little bit of a flicker? So we'll type a hash symbol, One more hash symbol, there it is. It's not even doing the flicker. How interesting is that? So the behavior is slightly different than it was on the other one. So under the cursor right now, there's nothing. There's actually just a space. In fact, I'm just gonna, for fun, type, well, I'll just hit the space bar, and we still see the 2. Now, as far as I can tell, it's not flickering either. And with the Siemens chip, that was flickering. That first character was flickering between what it was supposed to be and what was at the end of the line, especially if they both had a different character in them. But with that new Intel chip in here, that just does not seem to be the case. So I've typed out 1 through 0, and I did it 8 times. I wanted to just check that there were actually 80 characters across the line, and there absolutely are. The last 0 is getting replicated to the very first character, which seems a little unusual because we determined in part 3 that using that whole DME sequence that's coming from the CRTC, the MCU, or microcontroller, which is acting as the CPU in this case, is simulating the DMA hardware that would normally be associated with this IC. And that means that the CPU is instructing the SRAM to load the data bus all 80 characters across as it loads the row buffer into the video chip. And I think it was in part 2, or was it part 3? I don't remember. I actually swapped out the SRAM chip. This is the original one, but I put a different one on board just to see if that had any visible difference to what was showing up on screen, and it made no difference at all. So what the CPU is doing is when this chip is doing a DMA request for the first line of text, all the way across the top where it says like press quit for help or press help for menu or whatever it says. Well, we could see with the logic analyzer, because I was actually connected to this chip, that we were getting the correct contents of SRAM out. It wasn't like that first P was actually missing from that DMA request. I mean, we were looking at the actual data bus, right? That first P was there, and it wasn't at the end of the line. So I'm very confused as to why the buffer in the video chip is not getting loaded with that first row of characters, because it's there on the data bus. And what I don't get is I don't get how the last character on that line, or on any of the lines, ends up at the beginning of the buffer, because that's not what we see in the data bus as the ring buffer or the row buffer is getting filled. Now, if you can believe it, one thing I actually do have compared to the last part is we have access to the service manual. And this was graciously provided to me by Big Al, one of my viewers, who actually ended up buying this off of eBay, because I think there was a seller on eBay selling this, and scanned it for me. So it's up on archive.org. If you want to check this out for yourself, there's a link down in the description below. Now, one thing that's very unfortunate is this was supposed to have come with full schematics for this device, and it was not included from the seller on eBay. We do have new copies, better quality copies of the X-ray diagrams for both the modem and the main logic board. Perusing through the manual is mostly the same as what we saw in the owner's manual for this device. But here's a little interesting tidbit. It does talk about the differences between the different models. So I think this is a -A, and it says that the only real difference is the ROMs are different, and those differences allow for you to access different computer networks, which coincides with this ZT-1A, which has 188-1. That's what we have here for the source. And 162-1 is generic and used to access various networks, and then there's another version for prime fax. But check this out, we do have some additional info in the manual. Modes of operation. Mode 0 connects the modem to the terminal and vice versa. Mode 1 connects a TTL serial local computer port to the terminal and vice versa. The modem is not connected to the terminal in this mode. Then we have a mode 2 and a mode 3. Well, it appears that you can switch modes by hitting Control-Shift-F1 through F4, which was not mentioned in the manual whatsoever, the regular owner's manual. Not to mention, check this out, baud rates. While the modem is connected, you can only access 300 bauds, but in mode 1, do have these other baud rates. It looks like it's up to 2400. And then we have a whole section on the logic board. So I need to read through this because I haven't done that yet. Maybe there's good info in here about how the whole video circuitry works, and maybe we can figure out what's going on exactly. When the CPU recalls, the information is stored in RAM, places data on the address bus, which the CPU reads and processes, acting immediately on the command signal, placing the display information in the video memory, U126. That's the SRAM chip that I tried swapping out. The CRT controller takes the data from the video memory by interrupting the CPU and performing a DMA operation, which is what we looked at in part 3. The controller then sends the display data to the character generator, U135, and the character generator translates the parallel ASCII data into parallel character pulses. These pulses are converted into serial character pulses that the CRT can display by parallel serial shift register at U114. The serial pulses are mixed with horizontal vertical sync information. Yeah, this is all pretty much what I theorized about how it worked. Information from the keyboard is read by the CPU from the data bus, and the data has been read by U211 from the keyboard matrix. So those two extra small SRAM chips that are on the board, the little 214s, info out, memory full, stores info. Seems in a way it's like almost like a little bit of a scratch RAM or something. Video memory, that's the larger SRAM chip that we already talked about. CRTC with the CPU interrupt signal, that's exactly what we looked at. And then that all just drives the character generator and the assorted logic to generate the video signal through the shift registers and the horizontal sync pulses and whatnot that all come from the CRTC. It's relatively straightforward. The system RAM is made up of chips U124 and 125. Those are the two 1.4s, the smaller chips. And the CPU processes the data from the system RAM and stores display data in video RAM. When the video contents are to be displayed, CRT controller U134 sends a DMA interrupt through U128. U128 is the interrupt latch, which puts the CPU in a wait state. The interrupt comes through pins 12 and 13 of the CPU, is exactly what we saw on the past video, and the CRT controller activates the hardwired move instruction for the DMA process to begin, and the information stored in the memory goes directly to the CRT controller without CPU intervention. The CRT controller takes this ASCII information and sends it to the character generator U135, which produces the proper dot sequence, blah, 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 blah. Yeah, I mean, it's all what we already know. Scanline information is combined with vertical horizontal pulses. These signals come from the CRT controllers on pins 7, 8, 32, 35, 36, and 37, and are latched by U137, 138, and exclusively ORed by U133. They are then combined with open collector buffers, U131 and 139. The signals are sent to the base of Q101, which outputs the composite video signal to the CRT. Well, that's all working. That is all working just fine. The clock signal for the board comes from a 14.7656 megahertz crystal, which is divided down to 7.3828 megahertz by U142. Well, that's curious because I just looked and the clock that's on this machine, the crystal oscillator, is not 14.76, it's 12 point something. Maybe this is a different revision. We saw the clock signal that goes into the CPU is like 6.5 megahertz, which makes sense because remember I said it's like 12 point something is the master crystal divided by 2. And yeah, that's 6.5-ish. It's just talking about other parts of the board. There's voltage regulators, we know about that. The CMOS RAM, which we know about. U111 is a non-volatile RAM that stores important information such as phone numbers. The CPU is an Intel 8031 microprocessor, or really microcontroller. The program on the CPU is contained in 2 EEPROMs. Addressing of memory is from the CPU through U118. Memory mapping and I/O mapping for the CPU is performed by U116, the address decoder. Wait, there's a section on oscillator. What? Yeah, it's right here, 147656, and you become 7.3828. But then down here, it's a whole separate section. 12.96 is divided down by U142 to provide 6.48, and that gets divided again down for the 1.682 megahertz character clock for the CRT controller. That's what we see on this machine. Well, the information in this section is a little bit more technical, but it's weird that the clock stuff doesn't match what we saw up above. And there's 100% only one crystal oscillator on this board, and it's the 12 point whatever megahertz one that's mentioned right there. We do not have that 14 megahertz one, not on this board at least. It does talk about how reverse video works. I don't remember ever seeing reverse video, but I suppose it has that capability. It does also appear to have half intensity video capability with a highlight output on the CRT controller. This gates the active low signal, which decreases the maximum voltage of the output transistor. A 3-character pipeline or delay exists in the flow from the CRT controller to the CRT. U141 is the first character delay. U137 synchronizes the display coming from the CRT controller with those coming from U141. 138A is a second character delay, while 138B is a third delay. What is the delay there for? U128 is the latch that indicates whether the CPU is performing a DMA operation or not. The latch is set when the CRT controller is accepting DMA transfers from video memory under control of the CPU. For CPU to perform a DMA operation, U109 and 112 gate a move A, hash 74 instruction to the CPU data bus. The CPU provides the addressing from the video memory to be transferred to the CRT controller. When the DMA process is complete, the CRT controller puts its logic 0 on the DRQ, the DMA request line, and 128 clears, causing an interrupt to the CPU that stops the DMA process. Pretty sure that whole thing is working. U124 through 126 are video RAM memory that stores screen information. The RAM memory is addressed at locations 4000 to 4BFFF and 6000 to 6BFFF. The reason is that the DMA operations for the CRT controller occur at a different address than the DMA transfers for the CPU to the video memory. It says here that all 3 of the RAM chips, including the 2 114s, 124, 125, are actually part of the video memory. And the 1K of RAM that makes up those 2 sets of chips occupy, well, 2 different spaces in the memory space, 6000 to 6BFF and 4000 to 4BFF. So it's funny because up above it seemed to indicate that those extra 2 chips are not part of the video memory. That was on the block diagram that we saw up here. Doesn't really say that this is video memory at all compared to that one. This manual is a little confusing, some conflicting information in it. We have a section here on the CMOS RAM, the keyboard port, the printer port, and the bell. The bell seems to be derived from the clock signal that goes into the video chip, actually. Power going to the modem board, a lot of 5 volts DC, but we also have plus and minus 20 volts DC, plus a 12 volt DC. I have a feeling that's why this thing doesn't just use a standard DC power supply. It's using these AC rails on the power supply to create those additional voltage rails that the modem needs. The first half of the video RAM is located in U126. The other half is located in U124 and 125. If U126 is defective, you will see the top portion of the screen go blank. However, if you scroll the screen, the blank portion will jump to the bottom. It is confusing to me what they're talking about here. You know what I haven't tried is I haven't tried taking out these SRAM chips while the system is sort of in this working state just to see what it does. Because everything I was under the assumption was it was this chip, this 2K SRAM, that was holding the entire screen buffer. Apparently not. Well, let's just see what happens if we take out one of these 214s. That's half the bits. Let's just see what that does exactly. Well, that did corrupt the bottom of the screen. Let's see about the menu. Okay, well, how curious is that? It really does use that additional memory. These chips are 4 bits wide, so the one that's in here still is driving the bus correctly, which is why we have some characters that we have garbage that's flickering a little bit. It's because part of the data bus is floating. Well, so oddly, I'm pushing the quick key and that doesn't do anything. Okay, instantly, based on what the manual says, Control-Shift-Escape is the reset key. Because what happened is I got stuck in here. Pushing quit doesn't work anymore. That should just exit right out of the menu. I have to hit Control-Shift-Escape to get out of there. Oh, interesting, is without that chip in there, even the keyboard scan routines don't work. That's what's wrong. I'm pushing the down arrow and I'm getting the @ symbol. F key. Oh yeah, all right, well, so clearly these are also used for part of this keyboard scan routine. So that's just not working correctly at this point. All right, so now we're into the part of the memory that's using this RAM for the screen buffer. I wanted to see when I get to the end here, let me push something that will actually just type one character. Okay, when I type this last character, will that appear on the first character of this line? Yes, it will. So I really don't feel that the problem that we're seeing here has anything to do with the RAM, because when we were monitoring the data bus, which is obviously shared with these chips, so I didn't realize that some of the video memory was coming out of these chips, but it doesn't really matter because we were picking up the 8 data bit lines that then make their way into the CRTC for those DMA transfers, that is. And we know the problem, the first column is happening even on like the part of the memory that these are being used versus this chip. And we just confirmed that by pulling this chip out. So I think all of the SRAM chips are fine. And we know the data bus is being set up correctly with that entire line of text, including that first column that's going into the CRTC. So maybe what I need to do next is take the logic analyzer, we're gonna hook this back up and take a look at the character generator and see about what it's being told to display. We need to know, is that first column missing coming out of this chip? Or is there something wrong with the circuit after the chip? Where does the problem exist? I need to know so I can focus my repair on that part of the board. And turning this back on, and yeah, we're back to exactly where we were before, and I can exit correctly. And what happens exactly if I take out the character generator? We turn the computer back on, we just get a full white screen. So yeah, pushing help takes us into the menu, the cursor goes away, hitting quit goes back. Let's try to dial a number, A. Up in the top corner there, or we have inverted text, I suppose. And you can hear that modem is pulse dialing right now. So that's probably the part of the circuit that does inverse video that's coming from the CRTC and is going to the logic circuits that display the video. So that's how it's creating the inverted video. So I'm kind of curious about this character generator, the chip that I just took out. It's a 2516 EEPROM. That's a TMS 2516. Things are a little bit different on 2516 versus a 2716, which is a bit more of a common EEPROM that you can program easily. And you notice the biggest difference is the chip select line is pin 18. Sorry, it's kind of blurry. It's just this image I found. While it's pin 20 on the 2516. What if I stick a character generator from Commodore 64 into this machine? Will that work? Well, pin 20 happens to be chip enable 1, and pin 21 is chip enable 2, which means this chip is turned on when that is high. And according to this, pin 21 on a 2516 should be 5 volts all the time, and chip select is pin 20. Now this is half the capacity of the one that's on the 64, which means this address line is going to be fixed all the time. It's whatever this signal is, I don't know if that's 5 volts, probably is at 5 volts all the time. So that means that'll be high. We might get inverted text or something like that, but I'm thinking we should see something out of this chip when I pop it into the board. So let's try it. I don't think this is actually going to work. I think the characters that are loaded into this, even if we're not looking at the Petsky version, are going to be in the wrong position. So it's going to be kind of gibberish, but it should show a correct image. I'm really more curious just to see if we have the same problem where the first column of characters is still going to be replicated off the last character with the Commodore. This is a 64 character generator in here, 901225-01. So here we go, see what happens. Okay, well, obviously it works, and we're looking at Petsky, and obviously it looks like the way the lines are a little off or whatever, but we can see that it clearly does work. And what we can know for sure, absolutely without a doubt, is that first column is just as screwed up as it was with the other character generator. So it has nothing to do with this ROM that's causing that first column to be bad. And here's what I mean. I'm going to push A, and that did nothing. I guess this weird symbol we're looking at is the equivalent of the space character. And what's happening, the reason why it looks like it's B and then there's a blank and then we see a little bit more, maybe the next character like a top of a C or something, because this system has support for lowercase and descenders, which means it has a character cell that's bigger than the Commodore 64 character cell. And we know from what we saw in the logic analyzer that the original ROM that's in here obviously is using ASCII, and Commodores don't use ASCII, which is why the letters are all messed up. Anyways, the point being, as I type the A character on the first column, and we don't see it there, but if I go all the way to the end here, there we are on the last column, and I type A B appeared, which, yeah, is the A character. So we've 100% confirmed here that the problem with this missing column is not the character generator EEPROM. It is some other part of the circuit, or it's the CRTC itself, and because we have two CRTCs that behave in a very similar way, this has got to be a timing problem. It's just got to be, right? But I think what's really funny is if we go down to the bottom of the screen here, we know these bottom rows are coming out of these SRAM chips, these National Semiconductor chips, not this Hitachi one. And yet, we're having the same problem exactly over here. Somehow, the very last character on every single row gets loaded into the first character, at least in the ring buffer. And if I type in A, there it is. And yep, that is not coming from this SRAM, these two chips, or this Hitachi one. The problem is somewhere else. But what is it? Well, at this point, I think I have to break out the big guns. And what I mean by that is my viewer, Dan. For a while now, Dan has been reverse engineering both the ROM by hand disassembling it and annotating everything about the way it works, but also recreating the schematics from scratch. Dan started with the schematics recreation based on photographs of the board and that X-ray image that I'd shown on one of the earlier parts that was a photograph on some website. And now using the better X-ray images and component lists from that service manual that Big Al sent me, has been really hard at work recreating the schematics from scratch. It's a work in progress, but in this case, I think this might prove to be kind of helpful. Now, right off the bat, when it comes to the clock circuit, remember where we said in the manual that it was talking about some like 17 megahertz crystal oscillator? Really, the clock circuit on this one is that just under 13 megahertz crystal oscillator that is right here on the board, and that gets buffered and brought into this chip, which does all that dividing down and creates the CPU clock, the character clock that goes into the CRTC, and I suppose some attribute clock that goes off somewhere else on the board. And on this page, we have a latch along with the two ROM chips, and then there is the SRAM, the battery backed up SRAM IC. And on this page, we have a CRTC, that's the data bus input. This would be coming from the video memory. This is as it loads in all of the row data into it. Out comes the character data that's going to the character generator, the 2516 that we've currently replaced with this Commodore chip. These are the character counters. These are the 6 bits that control what character is being displayed. And then you have the line counters. And this thing has 4 bits for line counters, so up to 16 lines for each character that's possible. There are less of those on the Commodore chip, which is why the characters are kind of repeating over a little bit like that. The data lines come out of the character generator ROM into this 74LS166. That's the shift register that takes that parallel data, turns it into a serial bit stream that goes into this 74ALS574. I think that's a flip-flop or something like that, because we have a bunch of other gates that kind of loop around and do stuff. And out of that comes the highlight, the sync information. I assume the sync information is sort of fed in there. Then we have the pixel data itself, and that all gets combined, and then that's the composite video output. I do want to look at what chips it's talking about here are this delay pipelines. What if that's our problem? U141 is the first character delay, and 138A is the second display, while 138B is the third display. Those are 2 different units of the same IC. 141. So 141 is the shift register, and then that makes its way into 138A and B. So those are the 2 units. So that would be the first unit, probably pin 2. And then it looks like it comes out of Q0, goes into that gate, and loops around here and makes its way back into D5. And then that comes out Q5, and then that is the pixel output. That's the data stream that's coming out. So I suppose the propagation delays through these ICs equals about the width of 3 characters, but that would have the effect of moving the entire image over a little bit, as far as I'm aware. And it really feels like everything about the image is correct, even if it's moved over a little bit on the screen compared to, well, due to the propagation delays. I don't see any way possible that the pixel data for the last character could somehow wrap around and show up on the first column of the screen. There's just no way that that could happen. And the reason why I say that is because the delay that would be required from that last character, which incidentally, remember, shows up at the end as well. It shows up at the end and at the beginning of the line, is if somehow it was being delayed the entire time the beam was going back to the start, the scanning electron beam, it would be on the next row down. It wouldn't be at the beginning of the same row. And it is at the beginning of the same row. I mean, that pretty much rules out this entire part of the circuit here as being anything that could be wrong. Nothing is wrong with this part of the circuit at all. Nothing. Now this page right here, these are our SRAM chips used for the video display. So the large 6116 plus the two 114s that are used for that lower section. And then we have the LS245. So that's the bus transceiver that's connecting the CPU over to the video RAM. And then of course the video RAM is connected directly on these DB lines directly to the video chip. And we saw that right here. There are those DB lines. So that's all a shared bus right connected to each other. And we were able to confirm without a doubt that the DB lines are correctly showing the whole line of text, you know, with everything in the correct order and position. And again, I'm not finding a reason for that missing first column. And the next page here looks like it has something to do with the modem circuit. So we're not going to worry about that right now. Here's more modem interface stuff. There's our keyboard scanning matrix. So there's the 8x8 matrix on the keyboard, gets picked up by these 368s, and then makes its way onto the address data bus that then goes to the CPU. It was really curious to me how when I removed the SRAM chip that I thought was for video memory, remember it kind of screwed up the keyboard scanning routine? Well, these AD lines are not the same data lines that are on the RAM chips. The RAM chips, remember, are on these DB lines, so totally unrelated. In fact, this LS245 separates the AD lines, which is the CPU side with the keyboard and the modem, whatever serial ports and stuff like that, from these DB lines, which is the whole video subsystem and the SRAM. So the only conclusion I can draw from that is some part of this keyboard scanning routine is storing something in the 214 chips, like it's using a scratch RAM or something that is then getting messed up because I pulled out one of them, so those 4 bits got lost and it, you know, broke those routines. So the only conclusions I can really draw from looking through the schematics here is that this fault has to be with timing that either selects the CRTC or the ROM code itself is somehow the timing in it is just set up in a way that worked with this original really old chip. But these newer chips, both of these are newer processes, are somehow just not compatible. Now, when we take a look at the select lines, so there's the write line, CRTC write, and the select line, we need to take a look at those, where they're coming from. And then maybe I could try swapping out the chip and that'll alter the timing a little bit, like it will speed up the write timing, you know, when it goes high and it latches the bus. Here's the CRTC write signal. So it gets generated by PSN that comes from the CPU, address line 14 is from the CPU, and write 1. So DMA request that comes from the CRTC itself and goes through the flip-flop. We looked at that in the last video. It comes out, it goes to the CPU, interrupt 1 and 0, but interrupt 1 is actually over here. It's also going into this gate. Well, I've looked through everything on here and I don't find those signals. They're not here. I'm literally looking for this chip select signal for the CRTC, CRTC underscore CT or CS. This sheet's not searchable, unfortunately, this PDF. And I've looked through it, like I said, a couple times, and I cannot find what is generating those signals. So I know this isn't complete. Dan's been slowly working on this and making it more and more complete. Oh, there's that write 1 signal, incidentally. Well, it's coming from something. Where is it coming from? I'm not positive, but anyhow, like I said, Dan's been working on this and is slowly refining it. So I think it's just work in progress, and which is why I can't find that signal. I'm actually kind of suspecting that it's one of the address decoder lines that is that CS line, the chip select line for the CRTC, because I think it exists at address 7000 something or other. So it's probably that line right there that enables the chip. And if that's the case, it doesn't seem like that could be the issue because the whole system is working properly. All the registers for the CRTC get written properly into it, and that's fine. I mean, the data is being loaded correctly, just that first column. Every function of this computer seems to be working flawlessly, except for what's getting loaded into the CRTC. And it really just screams that this is some kind of a timing issue, like maybe with the setup on the CRTC or some parameter that's getting set up in there that's causing this particular fault. So moving on to the idea that maybe this is a setup problem with the CRTC, one of my patrons and supporters, Timo, had a conversation with ChatGPT OE or 3, one of the paid versions that I don't have access to. And let's just take a look at what the output of this is and see if any of this kind of makes sense. A one character circular shift, column 79 shows up in column 0, and every other character is shifted left by 1, almost always means end of row versus start of row timing is off by 1 character. I'm not sure this is actually what's happening, that everything is shifted over 1 character, and that's because it appears that the inverted character, like the flashing of the cursor and the inverted text, that's happening in the exact correct location. And that's done with hardware based on one of the other outputs of the CRTC. If where the cursor laid over the text was shifted over 1, like we had text that was off slightly, like it went off the edge of the screen by 1 character, I could believe it. Wrong horizontal total, that's one of those parameters that was loaded in when the system boots up and initializes the CRTC. So maybe video gating, blanking a shift register load is referenced the wrong edge. No, I don't see that number 2 is possible at all, again, because what we know for sure, because we swapped out the character generator ROM, is that the ROM is being instructed incorrectly, and that just comes directly without any logic in between it and the CRT. That's coming from the CRTC. And an address off by 1 in the VRAM, no, that's not right either. If the address was off by 1 in the VRAM, what would happen is the last character would show up on the next line, not on the same row like is happening here. So again, that doesn't make sense either. One of the other suggestions is count how many transfers the DMA transfer has. Well, we know that it's exactly 80, so it's definitely not that. I counted for sure, and it was 80 transfers. Saying that the first character should begin after the intended blanking interval for horizontal retrace. I can't remember what that looked like on the original video, but I'm pretty sure it looked completely fine. If the shift starts 1 character too soon, the last character from the previous line will be the first thing you see. Well, that is not the symptom. The symptom is not that. And the prompt says the last column of text is displayed as the first. The first column is missing or overwritten by the last column. Nowhere in the prompt did it say that it was offset by a line, but I guess it was thinking that was the case. So I'm not logged in, and this is a conversation from Timo's interaction with ChatGPT, but I'm going to try to correct it and say the problem specifically is the last character in the row is shown as the first, but it is also still shown as the last at the same time. This is on the same line, not the previous or the following line. Will this actually work? Okay, yes. The last character, column 79, is displayed both at the correct position and at the first in column 0. The true first character is missing or overwritten. This suggests not a wraparound or buffer indexing problem, but rather display logic error when the last fetch character is latched twice into the video shifter, once correctly at the end and once at the start. So it's thinking that there's like a wraparound buffering problem, but now I'm going to correct it again. Using a logic analyzer, I saw the exact data coming from the video RAM and going to the CRTC, and the data is perfect. There are 80 fetches exactly, and I could see the video RAM being fetched correctly with no wraparound or visible anomalies. Because remember, we saw perfectly in the logic analyzer exactly what was being loaded from the VRAM, and there was no problems whatsoever. So it's saying here that it seems that it's issuing 80 characters, it's fetching the correct addresses, applying the correct data, which is all what we saw in the logic analyzer. The problem is not with the 8275 and not with the video RAM addressing and not with the DMA. It means the issue lies in the video output logic after the character fetch. But again, I just don't think that's the case. I just don't see it. One thing about this is it has no idea what the schematics look like on the system, right? It doesn't understand the design of the system, which we've already reviewed. Us together have just looked at the schematics. It's thinking here that the shift register is what loads the character. It's not how that works. The CRTC loads the character directly from the character ROM. We saw it on the schematics. It's just directly connected. There's nothing in between the CRTC and the character ROM. The shift register has nothing to do with it. So I don't really think it's really worth going any further with this particular conversation because, we know exactly how this works, and we know that the only way we'd be seeing that character messed up like that is if it was coming from the CRTC, from these signals right here directly into that ROM chip. And that has changed quite fundamentally, to be honest, between this CRTC that's in here now and the Siemens one. The Siemens one on that first column was doing that flickery thing, but with this Intel one, it's not. It's perfectly solid, and it's just showing the last character again on both the last column and the first column. All right, well, I think I need to take a little bit of a break here. I'm gonna have to kind of think through what's been going on here and just try to figure this out. Maybe I'll reach out to Dan a little bit, who's doing all this reverse engineering work. Maybe Dan can whip me up a customized test kernel, for instance, or test ROM that is, that we can load into here, and maybe just display some patterns on screen, and possibly he can change the routines for the DMA requests, change the timing a little bit. I don't know, come up with some way to do some further testing, because We're clearly dealing with a very subtle bug that just might be that with an original chip here, one from 79 or whatever year this was, that this would have worked. It's just that I keep buying chips that are too new and potentially they're too fast, or there's just whatever, this timing issue is rearing its ugly head. Well, it's the next day and I've given some thought to what's going on here and what would be a possible solution. And I think where I'm going to go is I'm going to try to change the CPU clock rate. The whole section in the service manual where it talks about the 12.96 megahertz clock, which is the clock that's actually on this machine, contradicts with this whole section up at the top that says the CPU is running at 7.3828 megahertz. And if we take a look at my ZT-1 GitHub repo and we take a look at the photos, I have pictures of the ZT-11 that came from my friend Sark. And when we look at the backside of his PCB, well, remember that he has a little bodge board that adds that 7.3 whatever megahertz crystal that it mentions in the oscillator, and it feeds it directly into the pins on the CPU. Now, since the CPU on this machine is actually a microcontroller, it does support directly driving a crystal oscillator, which is, you see what's happening here. The crystal with a couple little tiny caps is connected to 2 crystal inputs onto the CPU because it's going to drive that crystal directly. Most normal CPUs, like say a 6502, it requires a clock input that's a TTL signal. It can't drive a crystal oscillator directly. So you have to have a little crystal oscillator driver circuit separate, which is actually what's already on this machine. Because remember, this has that 12 point whatever megahertz crystal, and there's a little TTL logic circuit that divides that down, and it feeds the 6.5 megahertz into the CPU on here on, I think, just one of those pins. And on the schematics, there it is, pin 19 and 18, the crystal 1 and 2 inputs. But if you want to feed a TTL signal into it, you just use pin 19, I suppose, and you leave the other pin disconnected. I'm going to operate off the hunch that perhaps the timing issues that we're running into are something to do with the DMA emulation that the CPU is doing on this machine. And perhaps when they designed this thing, they were using the very first revisions of the CRTC, this one, and it was a little bit more tolerant of the timing. So the way they set up the timing worked fine for loading the characters into the row buffers. But perhaps they quickly figured out that if you use the later revisions or the second source versions of these, like the Siemens part, it doesn't actually work properly. And maybe that's why they increased the CPU speed to speed up that whole DMA emulation routine and bodged on that crystal oscillator. The reason why they didn't just replace the entire crystal oscillator circuit is because that other oscillator, the 12 point whatever megahertz one that's on here, also feeds into the CRTC, and that's critical for the timing of the CRT output. And I'm pretty sure that the minimum, the ROMs that were on the ZT-11, because of that faster clock rate going into the CPU, they have to change some of the dividers for the baud rates. The baud rates are completely derived from the clock input into the CPU, and there's some dividers you can set. And obviously, changing the external clock going into the CPU is going to change the baud rates and make them not compatible. So I think what I'm going to do is I'm going to lift pin 19, so there's no clock input to the CPU, and then I'm going to use my frequency generator. I have this little Unity one here goes up to 30 megahertz. I will feed that exact 7 point whatever megahertz into the CPU on pin 19, and without changing the ROMs, we'll see if the system still boots up. We'll see if there's any difference with the way the DMA timing works. If nothing really changes, then I'm going to have to make a couple ROMs based on the dumps that Sark made on a ZT-11, and we'll give those a try. And I just bent out pin 19. I just want it to hang out of the socket, and I'll just clip onto it externally. All right, we have this set up for 7.383 megahertz at 5 volts peak to peak with a 2.5 volt offset. That just means the sine wave, instead of being centered around ground, actually goes from 5 volts all the way to ground, which is normal for a TTL type signal. And we'll be outputting a sine wave as opposed to a square wave. That just is a little bit easier because I'm going to be running this over clip leads. And the curved edges of a sine wave just work better than the sharp edges of a square wave. And the CPU should have no problem whatsoever working off of a sine wave. I'm pretty sure of that. So ground is connected to the ground of the large cap. That's the ground of the entire system. And then I have this red clip lead hooked up to the clock input, which goes to the clock output on the frequency generator. So I'm going to first turn on the output of my frequency generator, then I'm going to turn on the power to the system, and I expect to hear the normal beep out of the speaker. System beeped like normal. Okay, let's switch over to the video output. Is it going to look any different? No! No, that made no difference at all. That's amazing though that the system has no trouble actually running at the faster speed. It's like decoupled from the rest of the clock circuit on this machine, but I guess it doesn't really matter for the CPU speed. Let's just give it the old test. So I'm going to type an A as the first character, first few characters. And over here, I'm going to type B, B, B. And there we go, the B appeared as the first character. Yep, so it's acting just as it was before. I wonder how fast I can push the clock speed on this system. So if I turn off the clock, okay, the whole system got very unhappy. So we'll turn that off. I'm going to make it run at 8.3 megahertz. So we'll turn the system back on. Okay, it's running at 8.3 megahertz without any issue. Let's just change the clock speed while it's running. I can do that by just turning the knob here. Now it's running at 9 megahertz. Let's see, does it actually still work? Yeah, it still seems to work fine. Does that make the system any faster? I don't know. How about 10 megahertz? We're at 10 megahertz now. I'm assuming this is overclocking this little CPU. It still seems to work. How about 11? I assume we'll get to a point where it will stop working. 12. Still working. Amazing. 13 megahertz. Does that seem to draw the screen a little bit faster as well? Let's lower it way down to like 6 megahertz or 6.3. Yes, you can see how much slower it draws the screen, especially the top section than the bottom section. Then if I put it up to like 13 megahertz again, it just sort of all instantly appears. So you could totally overclock this thing. How cool is this? How slow can we go? All right, we're at 5.3 megahertz now. Okay. How about 4.3? It's getting slow, but still running. 3.3. It's chonky slow now. Chonky slow. How about 2.3 megahertz? Yeah, it works. Yeah, I wonder if like everything works. Oh, that was weird. Like how the screen blanked out for a second. Now, I think what might be happening there is I'm pretty sure with this CRTC, if the DMA transfer takes too long and the buffer underruns, it actually blanks the entire picture for a second. And I bet you that's what's happening. The keyboard routines are slowing down probably the ability for the chip to fill the DMA buffer as I start to type. And that just has an effect of blanking out the entire screen. And we're currently running at 2.383 megahertz. Well, that was a fun experiment, but it didn't fix our problem with the leftmost column being incorrect. So I think at this point, I need to go and burn those ROMs from the ZT-11 and try those in this machine. See if that fixes this problem, because I'm really running out of ideas of what might be wrong. All right, the ZT-1 ROMs are right here. I'll just swap them in real quick. Okay, they're in the board. These are really my last and best hope for actually fixing this problem. Oh, will it actually work? Well, let's see if this will actually power up. So I'm going to turn on the frequency generator along with the power supply at the same time. Okay, we got a normal beep. The reset sequence seems to work. And I'm kind of nervous to actually look at the screen output. I haven't looked at it yet. We'll be seeing it for the same time. And the clock is running at 12.96 megahertz right now, so not even the correct clock for these ROMs. But will this have any effect on the timing and fix this DMA problem? Let's see. Oh, it did not fix it. It did not fix it. I am so at a loss. It does say offline 6 at the top. That's a bit different. Let's take a look at the rest of the menus. Access code? I hit the help key. It said access code. What does that mean? 000. What? Help? 1, 2, 3, 4? What kind of ridiculousness is this? Oh, I'm wondering if this has like a password facility and it's saved into the SRAM. And since the SRAM on here was initialized by the other ROM, it probably got values in there, like some random junk for this password. Okay, well, obviously, I think one way to solve this is I'll just take off the positive lead from my battery here so that SRAM loses its contents. That should happen relatively quickly, and when we turn it on, it should do that factory default thing again. Okay, so I push help, it should say factory default. Oh, no, it did not. Fine, next step is I'll just take out this SRAM chip that stores these values. You have to kind of bend the capacitor out of the way to do that. Now if we turn on the system, obviously the help doesn't work. Oh, it wants us to type in a serial number? What? What? That's so strange. Hold save button and push enter. Well, that's not going to work because the chip is not installed. I just installed a different 2114 in there since I know we need something for this to work. Hit enter, press save. Okay, so there's the menu. They changed the menu a little bit. So the directory line goes all the way across now. It no longer has the vertical bars on the left and right. And that means that we actually have those characters in the very first column, but that's because the line goes all the way across the screen, all the way to the far other side. At the setup menu, does this look a little different? Yeah, I don't think we had stuff for parity. Mode 1 default, online. Mode 1, if I recall from the service manual, was the external serial port. So it almost feels in a way that when you switch the mode on here and then you save it, it actually retains that particular setting. That's kind of curious. That's a little bit different. Also, cursor blink is now actually saved as a setting. That didn't used to be saved as a setting. And you know what I also don't see? There's no clock anymore. The clock stuff is just gone. I guess they decided because this thing had no way to keep time when the power was off, they just did away with the clock entirely. Well, either way, this didn't really fix our problem. If we go to the very end here, the last one, I'm assuming should wrap around. Yes, there it did. It wrapped around on the same line. And with the Intel chip, we don't even get the flickering that we had before. So no matter what I type in this character space, it does not actually do anything. And for completeness, let's take the Intel chip out, the new Intel chip, and let's put the Siemens one back in. At least that had that little bit of flickering going on. And there we go. Yep, the Siemens chip acts a little different with that first row. It's flickering in a very strange way there, isn't it? That's kind of curious. And if we go to the bottom and we scroll the screen, that weird flickering stays there the whole time. So with the other chip, we would just see an R there. What's actually typed under that space where the R is the character 1. Let's try typing something else in, like a hash symbol. Wait, did that go away? Now it's not flickering? Oh, wow, it feels like it's conflicting a little bit there. Percent symbol. Let's try slowing down the clock dramatically. 6 megahertz, 5 megahertz, 4 megahertz, and now we're at 3 megahertz, 2 megahertz. Yeah, it still has the same problem when you type. It causes it to flicker out when it's at this extremely slow speed. But the DMA transfers are clearly running still because we're getting stuff on screen. If we bring up the menu, very slowly it comes up and it's working fine. All right, so I've only typed something into the first character and it's a Shift A, so capital A. Occasionally we're getting exclamation points there. And at 2.38 megahertz, let's turn the clock speed up. Does that change it at all? We're at 12 megahertz now. No, it really seems to sort of behave exactly the same, no matter what the clock speed is. Well, I've really entered grasping at straws territory here. I have zero clue what's going on here. Absolutely no idea. I think all I can do at this point is hook up the logic analyzer back up to the signals we were looking at before and maybe capture a few others, like chip select, which I don't think I was capturing last time. And let's try to see if we see anything out of the ordinary, and I can capture at a much higher speed with my new 32-channel logic analyzer, so we can really zoom in and try to look at all the timing, see where maybe there's a timing issue. Problem is, we've already reviewed all the data sheets that I have access to, and none of those have any kind of detail that will really help us. I'm under the impression that back in the 80s when this thing was designed, there was an Intel book that was much more detailed about how all of their products worked and interfaced to each other. And I have a feeling that was what was referenced in the design of this thing when they came up with the software emulation of the DMA access to the video chip. I'm thinking we have two possibilities. One possibility is these newer CRTCs, the two that I have, are a little different than the old original version, and the timing of the DMA transfer emulation is just not quite right. And potentially the hardware design of that whole emulation circuit along with the software on the CPU is maybe just not quite right for these newer chips. But the other possibility is that in the circuit that's emulating this DMA transfer stuff, perhaps one of these chips is too slow or too fast or just slightly out of spec or creates that timing issue with these newer chips. Without having a known good older chip to try, I really have no way to know if this machine is faulty the way it is right now. Like, is there an actual fault? Or are we dealing with a timing issue specific to the design of this circuit that just doesn't accommodate these newer chips correctly? I just don't know. The one thing I do know for sure is that the ZT-11 that my friend Sark has, where these ROMs, the ones that are on here, came from, it has the original chip, exactly like the chip that was in this machine that went bad. So if there is a timing issue that's in the hardware design of the board or the software, it doesn't seem like that was addressed necessarily between his machine and my machine. Well, for the third time with this machine, it's time for the logic analyzer. I have my new 32-channel logic analyzer connected up to the CRTC. And here's the capture I just grabbed. Basically, we're getting all of the data lines, the write line, the read line, the DMA acknowledge line, the DMA request line, the clock line, the chip select line, that's for the CRTC, the address line 0 that goes into the CRTC, and the horizontal retrace. I'm capturing at 50 megahertz, so we're going to be able to see all the detail we need to see, and I'm able to capture 500 milliseconds. In fact, I can capture a lot more with this new device. It has a much bigger buffer inside. I have the parallel decoder set up to decode ASCII just like we did last time, so we should be able to see exactly what's on screen. And speaking of on screen, I went ahead and typed all this into the screen. It was a little bit tedious. So on the left side, we have 1 through 0. 1 through 0 kind of repeats. And on the far right side, I just typed out letters on the keyboard. Now, unfortunately, the whole screen scrolled one line. So it started with a Q, but it's actually a W, E, R, T, and so on and so forth. And then, as you notice, I just typed some words into the middle. That way, when we're looking at a capture, we can just make sure that it's decoding the letters correctly. So on the capture, when I zoom in on it, I want to take a look at the end of one of the DMA cycles, because that's where I think the problem is happening. While the DMA cycle is happening, it's asserting the write line as it writes all of the bytes into the ring buffer. It should have 80 writes into the ring buffer. My hunch is maybe there's an extra write at the very end that somehow is causing the last character to wrap around inside the ring buffer. Now, the weird thing is about this particular problem is when you look at the datasheet for the CRTC, it's only expecting up to 80 characters in the ring buffer. So even if there is an extra write at the very end, it should know the DMA cycle is over and it shouldn't overwrite the start of the ring buffer. And because we're capturing 500 milliseconds, we're actually capturing multiple frames of video. One frame of video is about 16 milliseconds, and we're capturing 500 milliseconds. So there should be 25 DMA cycles that fills the entire frame, and then the whole thing starts again. And it looks like at the end, there's a little bit of something, and because you see some access to chip select that is on the CRTC itself, that means that the CPU is actually writing to those various registers inside the CRTC, so 80, 1C, 18. Now, when the system loads the ring buffer through a DMA cycle, that's what's happening right here. So it's loading in one line of characters into the ring buffer. Well, because that row of text actually makes up multiple scan lines, you actually have the horizontal retrace happening multiple times. So we can pretty much assume that when DMA request happens right there, that's the CRTC saying, hey, I need the next line of text. And there's the next line of text. And we can presume, since it's a circular ring buffer, meaning there's 2 lines, that as it starts to load the next line, which is what's happening here, the previous line that was loaded in back there is now what's going to actually be displayed through the character generator and the shift register on the CRT. And right now the clock speed is running at 6.5 megahertz on the CPU, and I can kind of presume that as you slow down the clock on the CPU, this whole DMA cycle slows down. But you'll notice there's a lot of room in between the DMA bursts. You see how the DMA request line just goes low for all of this time? Well, I think that's the reason why when I slowed the clock down, way down, this probably slowed down, like it would end up kind of taking up all this blank space here, but it didn't run into the next one. As long as it doesn't run into the next DMA sequence, it's totally fine. But then when I pushed some keys on the keyboard, I think that probably slowed the CPU down a little bit further because it was busy handling keyboard routines, and it probably slowed the DMA requests down so much that it started to underrun and bump into the next one. But running at the 6.5 megahertz, that's roughly the stock clock speed of this system, there's lots of space in here for these DMA cycles to actually happen. When the CRTC wants to load a line of text, it sets the DRQ that goes high, and then eventually DAC goes low, and then right at that point, that's when the CPU starts simulating the DMA request and loading the actual buffer. And after 8 characters, we have the DRQ line drop to low, and it does that every 8 characters. That's that burst rate that it's using, and the whole time the write line is toggling, the read line doesn't do anything, and the DAC line just stays low all the time. That means it's asserted from the very beginning of the DMA cycle, and it should do it all the way to the end. Well, let's actually go to the next line because we can actually see what the very last character is, because remember I typed it in. So there's our first line of text that I typed in, which is actually line 2. And you see there's the number 2, there's the word 2. Those are a bunch of spaces, that's 20. And if we scroll all the way to the very end, the very last character on that line is a W. That's what I typed. Remember, it was a Q, but it scrolled, so now it's a W. And notice when the W gets transferred into the CRTC, so the last write cycle happens right there. In fact, I'll just put a line there. So that's when the final W gets transferred. Well, immediately after that, the CRTC drops the DMA request line. It's deasserted. That's this dropping going down. So the DMA cycle is finished as far as the CRTC is concerned. It's had its 80 transfers, all the characters are there. It's like, okay, we're done. Well, the funny thing is the DAC line doesn't deassert for quite a while. It kind of goes all the way to over here before that turns off, which may or may not be a problem. I don't know. But I guess what the problem is look at this spurious write. Now, the funny thing is you would think the CRTC knows it's done. It's already deasserted the DMA request line, right? That has gone low. It's asserted when it's high, so that's gone low. So you wouldn't necessarily think that this spurious write would actually cause any issue. Well, the thing is, because DAC, which is an input into the CRTC, is still asserted, maybe somehow this extra write is confusing the CRTC, and it's, I don't know, taking the last character, which happens to be a W, and rewriting it into that first character in the ring buffer. Now, the funny thing is, when this extra write happens, well, you could see the character that's actually set up on the data bus is a space. It's not even the last character. And I bet you if we check any other line, it's going to be exactly the same every single time. So this is the next line down where E is the next character. And sure enough, when that spurious write happens, what's on the data bus at that exact moment is a 20. Well, it's not ASCII space that's written into the beginning of the ring buffer. It is this last character that it's still holding on to, I guess, when that write comes in. On the original datasheet for the CRTC, which is what we're looking at here, the write pulse width is minimum of 250 nanoseconds. And remember that the symbol is TWW. We got to go find that on the timing diagram. 250 nanoseconds for TWW. 250 nanoseconds is what that needs to be. Now, if we look at the write timing for the very last character, the E on that line, the width is 460 nanoseconds. So that's totally fine. That's within that 250, that the minimum required by the datasheet. But this write pulse here, let's zoom in a little bit, this write pulse here is 20 nanoseconds, far shorter than the datasheet specifies, so you figure it would just ignore this. And that makes me think that first version from 1976, the one that was on here that died, maybe this thing really didn't respond at all to that little pulse of 20 nanoseconds, and, well, this problem was always there on this hardware design, and it just didn't manifest itself. Well, these new CRTCs, like this one from Intel with a 1985 date on it, probably just runs a whole lot faster. The process on here is probably better, and whatever the transistors that are in there are working at a faster speed, so that little pulse is enough to cause this weird side effect. That to me is the only likely candidate for this particular problem. Now what's funny is I would think when I turned up the clock speed on the CPU that 20 nanosecond pulse should have been even faster, like maybe 10 nanoseconds, and we would get to a point where even this faster CRTC wouldn't respond to it. I think what I want to do is I want to turn up the clock speed. So we're at 6.5 megahertz. Remember the 20 nanoseconds for that spurious pulse. Let's double this to, it's like 13.5 megahertz now, and let's run the capture. Oh yeah, those DMA transfers, they seem a lot further apart, meaning they're not actually time-wise further apart. They just run a whole lot faster. And let's look at the end for that spurious write. There it is. And it's still 20 nanoseconds. Okay, that's interesting. How about these write cycles? So 220 nanoseconds, I think that's about half as much as it was compared to when it was running at half speed. So that's really curious that the width of this spurious write didn't change. Here, I'm going to run it at 2.5 megahertz. Let's see what the DMA cycle looks like now. Whoa! Yeah, that runs very slowly there. So the write cycle time is now 1.2 microseconds. That was 400 nanoseconds while the thing was running at the normal clock speed. How about our spurious write? Still 20 freaking nanoseconds. So that doesn't change whatsoever based on the speed. And I'm pretty sure that's what's causing our issues. Okay, I'm gonna really push the limit here, 14.5 megahertz. And we're still at 20 nanoseconds for our spurious write. Write cycle timing, 220 nanoseconds. We're approaching the limit. Minimum was 250 on the data sheet, or actually we're under the limit for the write timing. But I think that was the original chip and not this later, higher speed, faster process chip, or for the CRTC that is. Okay, so just for fun, I'm gonna see how slow I can make this before the system crashes, because I figure it will crash eventually. We're at 1.5 megahertz now. DMA cycle, yeah, I think this is broken. How slow are these write cycle times? 2 microseconds, very slow. We still have our spurious write though at 20 nanoseconds, all the same. There it is, yeah, that's clearly not working. Let's put it up to 2.5, see if it fixes the problem. No, yeah, I crashed it. Oh, there we go. I switched it to 3.5 megahertz and it just blipped back into existence. Okay, well, my hypothesis is that spurious writes at 20 nanosecond write happening at the very end with these newer chips is being picked up, and that's somehow causing that loop to happen in the ring buffer. And obviously this Intel chip is more susceptible where it shows up perfectly, but the Siemens chip, which is what we're looking at now, we have that flickering going on. And we have to assume this is a design quirk with this machine, and with the old original chip, it just ignored that spurious write, and that's why everything worked, and the designers just left it in. And in case you're curious, here's the oscilloscope hooked up to the CRTC write line. So all these write pulses up at the top, that's the actual DMA cycle. And there is that extra little write that is happening that we think is causing all of our issues. In fact, let's just turn off the bandwidth limit here and let this go to full. And there we go. We can see that it really is going all the way down to ground. If we use our cursors, we should be able to get right around 20 nanoseconds. It's hard to know what this signal really looks like in the analog domain, but there we are at 19.9, so about 20 nanoseconds. And I think the threshold voltage on my logic analyzer was set for around 2 volts or 2.2 or something like that. And well, that's 2 volts right there, so we're pretty close. So Dan went ahead and sent me a revised copy of the schematics. This is A, searchable, so I can select the text on here, but B, actually has a few small changes, some clarifications, and a few other minor things. So let's go find the CRTC write line and see where that is coming from exactly. So there it is, pin 10, that's the write line, CRTC WR. All right, and doing a little search and replace brought me right to that in the schematic. That's so much easier than it was before. So the signal, CRTC RW, is based on these two gates. I think it's an AND gate and a NAND gate. And looks like this one is hooked up to write line 1. That comes from the CPU, and I think it's buffered, which is why it's write 1. And then address line 14 goes into the NAND gate on pin 2. PSN, that comes from the CPU. I think it's through a buffer though. And then we have pin 13, which is the output of the flip-flop that's based on the DMA request line. I just fired up Logic Friday and I added the two gates so we can kind of look at all the combinations of these gates that result in the outputs either being 0 or 1. We're only concerned about the output going to the CRTC being 0. Anytime it's 1, it doesn't really matter. And you'll notice there are various situations based on all these different combinations. When the output of the gates is 0, that instructs the CRTC to pick up the data bus, basically write to it. Now, I'm not really smart enough to know which of the inputs and outputs that are resulting in the CRTC write pulse being low for that spurious little bit. I think what I'm going to do is hook up the logic analyzer to the 4 inputs and the output so we can just look to see where we get that little spurious write, to see which situation on the input side is resulting in that. All right, here's where we are. So I decided to just keep everything hooked up to CRTC, and I just clipped onto the 2 chips that are relevant with those extra gates so we can look at all the relevant signals. And that means specifically we're getting the PSEN line, that's pin 1. Then we have pin 2, which is address line 14. That's 17 there. We're picking up on pin 13, interrupt 1. That's this red one. Then we have the output of the NAND gate. That's pin 12 here that goes between the 2. I just want to see what that looks like. And then we have write 1, which is this line that's going into the AND gate. And the output we already have because we're picking that up here. Where is it there? That's the write signal. I should just change that to CRTC write so it's a little more clear. And if everything is hooked up correctly, then theoretically we should be able to see all of these inputs and we'll be able to see exactly what's causing that spurious write to happen based on the inputs of these gates. So I'm going to turn on the crystal oscillator, start the system, hit play, and let's see what we see. Okay, so here are the write cycles, the DMA write cycles. There's that spurious write, 20 nanoseconds. It seems to be related to the output of the NAND gate, because that's the 20 nanoseconds. I guess that's just propagation delay that makes it through the AND gate that comes out to the CRTC write signal. But what's causing that? My only hunch is that the transitions that we're seeing here, there's something going on in this little tiny gap of time that we're not seeing. I'm going to turn up the speed. Can I go faster? 100 megahertz. Yes. I still don't understand what's causing this. I'm just rearranging these so they're in the right order. So interrupt 1, that's on the top. So interrupt 1. Then we have address line 14. And pin 1 is PS enable. That goes into the NAND gate. So PS enable. And then the output of that is the NAND output, which gets ANDed with write 1 signal. And then that creates the CRTC write. I'm just modifying the gate diagram to add the NAND output so we can kind of take a look what exactly that looks like. So anytime the NAND output is actually 0, all the inputs have to be 1. Which according to the logic analyzer, that is not the case. That is low, high, and high. So even though we don't see it here, this interrupt line must be slow. So I took a little screen capture because I'm just going to try to annotate on top of this. So I'm wondering if what's happening is the interrupt line falls slowly and this thing rises fast. And what happens is there's a little bit of an overlap time right there where it thinks that all 3 of these are high because of this sort of slow fall. Like maybe it's something like that. And that results in this part right here, this pulse coming out of it. And maybe 20 nanoseconds is like the minimum amount of time that it can actually be pulsed. But even though these are never actually in that state for 20 nanoseconds, and maybe it's just like this tiny fraction of a second, so that creates this pulse, which then makes its way with propagation delay through the other gate, and that's the 20 nanosecond pulse we actually see. I'm kind of feeling like maybe I should just replace this chip, the NAND gate, because it definitely is coming from the NAND gate. And maybe just a different brand will have the effect of just getting rid of that pulse, just due to like different threshold values on these signals that are going into that gate. In my spare parts, I found this 74LS10 Schematics part from 1984. Let's see if this makes a difference. I have the clip back on there. Let's search for that spurious right. We still have it. There it is, 20 nanoseconds. It looks different here because obviously, unless I was misreading the capture before, people were screaming at the screen. Remember, we're gonna get this output low when all of the inputs are high. Well, there's obviously this space right here where they're all high. And yeah, I must have been reading the other capture wrong, because yeah, anytime the inputs to an AND gate are all high, well, the output's gonna end up being low, which is what we get here. But now this kind of makes me wonder, if we replace the flip-flop that's generating the interrupt 1 signal and we put a faster one in there, or like a newer one, maybe moving this transition from high to low over a little bit, if it goes faster, would actually result in this pulse going away. Either that, or we gotta slow down this PSN by adding an extra gate in there. If we put another gate in there, I suppose this transition from low to high would happen over here, and then that wouldn't cause this little spurious pulse. So I'm just gonna put back in the original 74LS10, and we do another capture, and we go find our little spurious right. And yeah, never mind, it's right there. I don't know what I was thinking. We have a high, high, high right there, which generates this low output, which generates the spurious right. Okay. The amount of time we're dealing with is between these 2 points, and I'm pretty sure that is 10 nanoseconds or so. Because I think the entire time right there, yeah, this is 20 nanoseconds, and you can tell this one is sort of in the middle of that. So 10 nanoseconds. And if we're talking about PS enable, it's going from low to high. Well, maybe I could put a capacitor on there to try to slow down that rise time such that it more lines up with interrupt 1. I'm going to spend a moment to fiddle around, swap out some chips, add a capacitor here and there, and see if I can affect this timing here to try to get rid of U132 NAND output. Yeah, I've renamed the outputs here just to be a little bit more clear. Now, I haven't made any modifications to the board. There are extra gates on the board that I can use to try to slow down the signal, the interrupt 1 signal. I have a 1000 picofarad capacitor between ground and that signal on the NAND gate. Let's just see if that makes a difference. No, that didn't seem to do anything. Oh, wait a second. There is a difference. We're on the Siemens chip, and if we go all the way to the far edge and we type letters, it doesn't even appear on the left side anymore. So that actually, that changed it. Now I had to unplug from U132, so I can't do a logic analyzer capture, but I still can capture the right line. It's not 20 nanoseconds anymore, it's 160 nanoseconds. And that has an interesting effect on the system. That absolutely had an effect. No matter what I type over on the far edge there, we no longer get the flickering or whatever. We just don't get anything in that first character at all. And I think what's happening now that that right pulse is longer, 160 nanoseconds, is actually capturing what's on the data bus. And the data bus at that point is a space, hex 20. It seems that when this pulse was really short at 20 nanoseconds, it was actually capturing what was in the last character on the row, and it was putting that at the beginning of the row buffer because it looped around. But now that it's longer, it's actually capturing what's on the bus at that point, which happens to be a 20, and it always is 20. That 20 sits on the data bus for quite a while before the data bus sort of changes. I don't know, other stuff is going on, like some of the RAM is being accessed or whatever by the system. But yeah, it sits there at 20 for a while, and that's what's getting written into that first character when it loops around. Well, you know what? This is actually a good thing, because this confirms for sure that that extra right pulse at the end is causing this problem. And I guess because it's really short at 20 nanoseconds when I don't have the capacitor on there, that has the effect internally on the chip of it looping around to the beginning of the row buffer. But I guess because that pulse is so short, instead of it picking up what's on the data bus, which is a space, which is what it's doing now, it just picks up what was last on the data bus, which happens to have been the last character on the line. Very interesting. So that tells me exactly what I need to do at this point. I need to modify the signals that go into that NAND gate that create that spurious pulse to make sure they're never in a state where they're all high, where the NAND gate is outputting a low right signal when it shouldn't be. I always need it to work when it should be working. I just need to get rid of that slight overlap there where we're getting that spurious output. So I need to give some thought to how to do that. I think it's going to involve using some extra gates, and I think there are some extra gates on here. I just need to kind of think through the right process on how to do this, and I'll be back. So this is the flip-flop, the one that I'm going to try to speed up. And to make that happen, I found a scrap board that had a 74F74 on it. This is the same flip-flop, but instead of an LS part, it's an F part. And these are much faster, way more than 10 nanoseconds faster. Now, generally, fast parts don't always play nice with LS parts. These things are so fast, they snap the signals up and down really quickly, and that can cause noise and other artifacts. So this may just cause this whole thing not to work, but let's give it a try. So I'm going to turn on the clock source, and here we go, 3, 2, 1. Press help. Unfreaking believable. I cannot believe it. Oh, it actually works. I cannot believe it. I mean, I believe it because it makes sense based on everything I saw. And wow, just wow. I cannot tell you how many hours I've actually been working on this. When the video was all edited down, I know it's been multiple episodes, but the reality is there's a lot of footage that I actually record, and it takes quite a bit of editing to get this down, even into like the 1 hour episodes, like the one you're watching right now. So I feel so freaking good knowing that I was able to analyze the problem, figure it out, think through it, and actually figure out what the issue was. Oh, I cannot believe it. It freaking works. Whew. I am so relieved, frankly, so relieved. Now, I had sort of alluded to this before, but if you look at the schematics that Dan had come up with, there were several unused and OR gates on this design. Not the most efficient use of all the TTL gates. If this hadn't have worked, then I was going to take that PSEN line that was going into the NAND gate and feed it through one of those extra gates, which would have added hopefully about 10 nanoseconds of extra time on it. The 10 nanoseconds should have had the effect of also eliminating the overlap, just like I did by swapping out the flip-flop just now. Now, the problem is with using those gates is I would have had to do a bunch of bodges on the board. So I would have had to cut around the pins that are on the socket, because a lot of times those leftover gates, they actually ground the inputs because you don't want to really leave them floating. So I have to cut the grounds away, and then I have to run some flying bodge wires across the board or whatnot to add that gate in line with that signal that's going into the NAND gate. So I'm really relieved that F74 worked in here, well, at least seems to have not affected this thing in any negative consequence, because of course I didn't have to make any changes to the board whatsoever. All I had to do was just swap that chip out and we're good. And I still have the original chip here, which I can just leave with this thing if someone ever wants to restore this back to its original configuration. So now when I press the help key, it asks for the serial number with an S. There's actually an S there. You just type whatever, hold the save button down and push enter. There we are in the menu, and it says press quit to exit. This is actually working. I freaking can't believe it. I still can't believe it. 100%. The entire problem with this machine from the very beginning was, well, there were three things. The tantalum shorter that took out the power supply, so that's unrelated to this problem. The CRTC, the Intel CRTC, had failed, so I swapped that out with the Siemens part, which incidentally is what's in here right now. And the final problem was a design flaw that all of these machines are going to have from the very start. So I have to imagine if anyone else has a ZT-1, ZT-10, or a ZT-11, and you swap out the CRTC with anything more modern except for this very early Intel one that was on here, it's going to have exactly the same problem. Because when the designers made this thing, I guess with this thing in there, it actually worked, but that little spurious right pulse there was just ignored by that one, but not ignored by these other chips. And what an interesting quirk of the 8275 CRTC that the ring buffer can get overwritten on the front with additional right pulses. I have to wonder if there's anyone out there watching who's familiar with this particular CRTC, has ever seen this particular problem, and would have thought that extra right pulses after the DMA sequence was completed would result in the ring buffer wrapping around like it was doing. And there it is. The leftmost column, every single row has a character typed into it. I can type stuff on the far edge on the side. It doesn't matter. It works completely perfectly now. Let's run another capture, even though this thing is now working, so it doesn't really matter what this thing looks like. Let's zoom in on the end. Oh, there is still a spurious right. How freaking curious is that? And it's still 20 nanoseconds. But we have a working system. So that's the K line that I was looking at. Well, just to satisfy my curiosity, let me hook up the rest of the inputs here so we can see these lines like the interrupt lines and what's happening on the NAND gate. Okay, extra lines are hooked up. We can see them doing their thing now. There's the first line. It says press. Let's go to the end. All right, well, actually, nothing looks different here at all. The interrupt line is still overlapping with the PSEN line, just like it was before. It looks like it's about 10 nanoseconds worth of overlap. And we have our NAND output pulse, and we have our CRTC write pulse as well. Well, I don't fully understand, because it's clearly working, and yet we still see the same issue with the spurious right. So I guess that means I was completely off base, and this flip-flop was just bad somehow, and yet changing it out with a fast one just fixed it? Well, you know what we can do? Is I happen to have another flip-flop. This is the one I just took out of the board, but let's take out the fast one, and I have another LS part over here. Yep, this is it right here. It's another TI part, exactly the same as the one I took out. Let's put that one in. Well, the legs are kind of tarnished on this one, but that should be fine. And let's see if it magically works with this one, which is an identical part to the one I took out. No, it's back to not working again. Yeah, so this obviously is a problem to do with the flip-flop. Let's see if I put stuff at the very end. Okay, and it's showing a J. Oh, and it's even doing the flicker thing. Okay, cool. We do have the Siemens chip in here. So again, that confirms that this part, the one I took out, is not bad, and the one I put in here is not bad. These are both good flip-flops. Okay, what actually is bad is the one I just put in. The leg just fell off on it. I guess that tarnishing is a little bit more than tarnish. Yeah, there's the leg that came off this chip. But let's pop back in the 74F74, the fast one. Fast, it actually is fast. These ones are really quite fast, actually, compared to these. They run way faster. I think I saw that the propagation delay of this regular one that was on here was maybe 20 to 30 nanoseconds, and this one is more like 6 nanoseconds. And yes, with the fast part in there, it totally works. Why it's working? I don't know. You tell me. Well, I know this was a pretty long video, and frankly, I thought I had zeroed in on exactly what was wrong. I did, kind of, but I still don't exactly know why it's working now versus not, because when we look at the logic analyzer output, we still see that extra right. The only thing I'm thinking of is that maybe, even though the pulse looks like it's 20 nanoseconds, maybe it's actually less now, and the resolution of my logic analyzer is not able to show anything less than 20 nanoseconds. Actually, you know what? That actually might be the case. I was doing the capture at 100 megahertz, and 20 nanoseconds is pretty fast, and it's quite possible at 100 megahertz, it just can't resolve anything less than that. So the pulse probably shrunk because the overlap shrunk, putting this fast part in there. It still looks like it's 20 nanoseconds and there's still overlap, but I have a feeling if there's still an extra pulse, it's probably much shorter. Oh, let's try the oscilloscope. I know I need to end this video, but I just want to try to figure out what exactly is going on here. Yes, the pulse is absolutely there, but it's definitely shorter. So the cursor delta is 19.8 nanoseconds, but you can see that this is much more like 13 nanoseconds now. And I guess that is beyond the capability of the CRTC to be able to trigger off of. So the faster flip-flop didn't eliminate the spurious right, it just sped it up. And I guess it sped it up to the point where the CRTC was okay with it. I mean, that's how this thing left the factory with that extra right there. It's just the old CRTC was okay with whatever 20 nanoseconds that was there, and these new ones weren't. So we just shortened that down, and now even the newer ones are okay with it. Well, at least the Siemens one is. So as far as the Zenith ZT-1 goes and this repair exercise, all I can say is, wow, I never expected this thing to be so difficult to get working. And to be honest, that really comes down to the fact that I'm not a hardware designer. I'm just a hobbyist here. I don't really know what I'm doing when it comes to hardware design. And I bet you there were folks watching who were hardware designers, especially back in the 80s, and ran into issues like this all the time and know a lot about propagation delay and having to add gates or take them away and add capacitor here or there just to kind of get everything working just perfectly. Because clearly, like, this design was working on the edge, even like the way it left the factory, and the fact that it was so close to the edge got exposed by the new CRTC. And I remember hearing stories about that all the time, like even with the Commodore 64, like where certain specific brands of certain chips wouldn't work on the board. You had to use other brands. I think these types of edge timing cases happened all the time back in the day, at least with designs like this using all discrete TTL logic. Now for me personally, and I hope for you, this has been an amazing learning experience, especially because I really got to learn how to use my logic analyzer, and I'm feeling a lot more confident with it. And I feel like in the future, if I run into weird issues like this, hopefully I can try to get to the bottom of it with this tool in the future. But I do want you to keep in mind that I have repaired hundreds and hundreds of things, and I've never needed to use my logic analyzer once to actually affect any of those repairs. I was always able to get to the bottom of it with regular tools like an oscilloscope, multimeters, things like that. But I also think the reason for that is I'm not trying to troubleshoot design problems, which is why I haven't really needed to use the logic analyzer. I'm trying to diagnose faults, but the faults usually creep up because a chip is bad or whatever, and you can figure that out and fix it. Clearly at the end here, once the CRTC was replaced, the whole time I have been tracing down a design problem with this thing when it came to the way the logic was laid out by the original designers. And what's kind of amazing to me is in 1981, when this thing was designed, they didn't have these digital logic analyzers. I actually don't really know how you would go about trying to troubleshoot issues like this, other than trial and error and familiarity with the data sheets for all the ICs and a really good comprehensive understanding about how the propagation delay goes through TTL logic and timing diagrams and how to compare them together. And I'm not actually sure, as I really don't think there were tools like logic analyzers at that point, or if they were out of reach of pretty much everyone. So if you were a hardware designer back in the 80s and you were running up against issues like this, how did you solve these things? When I look at the original Amiga design, the breadboards and wire wrap and all that, how did you solve for timing issues on that stuff when you didn't have access to tools like this? As far as the ZT-1 goes, I do want to do more with this machine, but I need to take a little bit of a break. This thing has consumed a lot of my time, and I think people are probably going to want to see something else on the channel for a little bit. Don't worry, I will definitely revisit this because I want to get this thing working with the serial port. I want to test out the modem. There's definitely more to try with this thing, and I've spent so much time with this now, I really need to see it fully operational, so I fully intend to get there. I really want to give a huge thanks to Dan, who came up with the amazing schematics for this. If it wasn't for Dan, I'm not sure I would have ever been able to figure this out because I would have had to reverse engineer all that stuff myself, or maybe the schematics would have appeared at some point online. I want to mention as well that Dan has fully reverse engineered the ROMs for this, and I'm going to post the disassembly of those on GitHub. I just need to get his permission first. It's an amazing, detailed work that Dan did, and if you want to see some of the clever things that the designers did with this, it's pretty interesting to read through his disassembly. And I think that's going to be it. I hope you've enjoyed the journey that I've been on with the ZT-11 and getting it working. I've definitely learned a lot. Hope you did too. And I guess that's going to be it for now. If you liked it, thumbs up, subscribe, thumbs up, thumbs down, you know, all the usual YouTube stuff. And huge thanks to my supporters. And that's going to be that. So stay healthy, stay safe. And I can't believe this freaking works. I'll see you next time. Bye.